kind of see what I'm doing today. All right, so anyway, um, well, let's go ahead and get started. We're just going to try to finish up chapter 10 today, and then we move on to chapter 11 next week. And that puts us into another exam once we're finished with chapter 12, which will be toward, do you see, 22nd, 23rd, 24th, 25th. So I guess we'll finish chapter 12 a week from now or so. Like a week and a weekend. But then we'll have an exam for chapters 7 through 12. That will be due at the beginning of August there. And then we'll essentially just have 1 week left of work. Just crank out a few things in chapters 13 and 14 and we'll be done. Take a final exam and be done out of here. So if there are no questions, let's move on with it and see how much we can get done here. So even though we're just doing one section today, it is a fairly important section. The last thing we studied last week, yesterday, was the macroscopic description of an ideal gas, which essentially brought us to the ideal gas law equation, or the ideal gas law, they call it. And remember that you could use this on a gas at any particular time, or you could also use it between two different states. In other words, it goes from one set of variables to another set of variables. It changes pressure, changes volume, changes temperature, whatever. You can even change the number of molecules. And then you would use a ratio version of this where you put the final over the initial or initial over the final and plug in all the stuff you know from two different points in time, two different states of the gas, and so on. Section 10.5, we're going to study what is called the kinetic theory of gases, which is almost the opposite of 10.4. In 10.4, we're looking at the gas as just a big thing of stuff, a big tank of stuff, and we just look at the big picture. We look at the pressure, we look at the volume, we look at the temperature. The only thing that we even consider as far as the small picture, like atoms and molecules, is just the number of atoms and molecules, and even then it's just kind of an estimate. But in the kinetic theory of gases, we start with one individual atom or one individual molecule, and we figure out what one molecule of gas will do, and then we build from there up to the big picture. So we're going in the opposite direction. And this is actually a very important theory because it helps us to establish what temperature actually is. This is actually one of the things that really helped us to establish absolute zero, for example, the Kelvin temperature scale. It helped us to figure out how we were going to cool down gases to near absolute zero using lasers and everything else. It's a very important theory for modern science. So there are 5 major assumptions that we're going to make for this theory. Now, all theories always start with what we call tenets, or these are the things you're going to hang the theory on, in other words. And these are usually things that cannot be disobeyed or disavowed or ignored in the theory. They're things that we're going to start with. They're the things that we're going to assume to be true at the beginning of the theory. And if our theory ever contradicts these things, then we have to throw our theory away or fix it, right? Every good theory has a set of these tenets or assumptions or these kind of laws that we start with to say these are the things that are going to govern how we do our theory. If you don't start a theory this way, it's guaranteed your theory will be junk. Guaranteed your theory will fall apart and have so many holes in it that it could never stand on its own. So, here are the 5 assumptions of the kinetic theory of gases. The first one is that the number of molecules in the gas is large, and the average separation between them is large compared with their dimensions. So in this theory, essentially what they're saying is that we have so many atoms or so many particles, and they're so far apart that they're not going to interfere with each other, and then we can treat their behavior using statistics, using averages and means and distributions, other things like this, and it's going to be a hugely important assumption. Number two, the molecules, the individual particles, obey Newton's law of motion. But as a whole, they move randomly. So if you look at a single particle, you could treat it just like any other particle using Newton's laws. But if we look at the whole picture, the entire gas, these things are going to look like complete randomness. Okay? Again, this means that we're going to be able to use some probability mathematics or statistics. Number three, the molecules interact only through short-range forces during elastic collisions. Okay, so if by chance, if there is a possibility that two of these particles do bounce off of each other or interact with each other or something, it is going to be a short-range force that causes this interaction, so probably just a little bit of electrical traction or something, and it will be an elastic collision. In other words, all internal angular momentum and all internal kinetic energies will be conserved. Okay? And what this is going to do is it's going to cause the gas to not lose energy through frictional forces and other non-conservative forces. Right? So all those collisions that might happen will be elastic and will conserve our kinetic energy internally. Number four, the molecules make elastic collisions with the walls of the container they're contained in. So whatever the walls are or the boundaries are of the system, whenever the molecules come in contact with that will be an elastic collision. We will not lose energy. Number five, all molecules in the gas are identical. So we're not going to have mixtures of two different kinds of molecules in a single gas. We have to make these assumptions, again, because it's going to make the math doable. So, let's start off with our single particle. Here is our single particle, and we put it inside of a small box. And this box has sides of length d. The particle has mass m. It has some velocity off in some direction in three-dimensional space. Who knows what direction it's going? And it has a velocity in the x direction, the x component of that velocity right here. So those are all the things we marked. Notice that we have x going off to the right, y going straight up, and z going off to the left here. Kind of off to the left. And what we want to do now is we want to assume that this molecule is going to collide with one of the walls of the box, and it's going to bounce off of that wall with an elastic collision, so it's going to bounce off with the same momentum that it had going into the wall, except in the opposite direction, or the same velocity in the x direction, except in the opposite direction, right? And so what we want to do is calculate the change in momentum of that particle. And what you do is you take the final momentum, which is going to be mvx, and you subtract off the initial momentum, which is negative mvx, because they're opposites, and you get the change in momentum to be 2 times mass times the velocity of x. So the change in momentum is actually twice its momentum if it has a elastic collision with the wall. Well, we also know that force is equal to a change in momentum over time, change in time. And so we go ahead and write that. Our change in momentum is 2 mvx divided by the change in time that it takes to do that. Well, how long does it take to do it? Well, we just figure if it goes across the box, bounces off the wall and goes back, we'll use that as our change in time. It's distance, it's time to get across the box. Well, time is distance divided by velocity of x, and so we go ahead and put that in. 2 times the distance divided by the velocity of x for the time right down here, and that ends up canceling out with the 2 up the top, and we end up with a 1 over vx, or a d over vx, and the 1 over vx goes up to the top as an mvx squared now, and we get that the force exerted on the box is the mass of the particle times the velocity squared in the x direction, so this is the force in the x direction obviously, and divided by the size of the box, d. Well, what if we have a gazillion of these particles and they're all hitting the side of the box that's on the x, that's parallel or perpendicular to the x-axis? that means we'll have to add up all of the forces from every particle. And since all their masses are the same, and all their little boxes can be the same, it's only their velocities that are different. So we just put in all these different velocities in there, and we add up a gazillion of these things, and that will tell us the force across this entire face of this container that has these gazillion particles in it. Well, what if instead of adding up all the different velocities, we just average all of their velocities, and then we can get an average force across the box? And so that's what they do here. They add up all the velocities that are squared, since in the equation it's velocity squared. They add up all the velocities of all the particles in the x direction squared. They divide by the number of particles, and they get the average velocity squared of the particles in the x direction. And then they throw that into the equation, and this now is going to be the total force on the wall using the average velocity squared times the mass of the particles. You have to multiply by the number of particles, because the force has to, you get the same amount of force from every particle, so you have to multiply by that number of particles. Then we divide by little d, which is the size of each one of those particles' domains, you could think of it as, their little space that they live in. So that's the force just on a single wall in the container. Now we also have to realize that each one of these particles doesn't just have a velocity in the x direction. They also have some velocity in the y direction, some velocity in the z direction. So in other words, their x direction velocity on average is only 1/3 of the average velocity. And so we take that relationship, velocity squared in the x direction average, and this little bar over the top means average, by the way, and equals 1/3 of the total velocity squared average. And then we can get the total force on the walls of the box is going to equal n over 3 times mv squared over d, where v squared is average velocity. And if you want to calculate pressure, it's just force divided by area. And since the area of our box is d squared, we just plug in force divided by d squared, and it's going to have the 1/3 in front. It's going to be n over n over d cubed now, because there's a 1 over d in this original force equation. We solve this through and get pressure. Ends up equaling 2/3 now, n over v times 1/2 mv squared. Why did they make it 2/3? So they could put a 1/2 mv squared here, which is kinetic energy. So what is the end result? The end result of this theory, well, it's not the only end result of this theory, but it's one of the end results of this theory, is that the pressure and the kinetic energy are directly related to each other. Pressure is equal to 2/3 times the number of particles over the volume of the container times the kinetic energy, average kinetic energy of the particles. So pressure and kinetic energy are directly related to each other. Obviously what this means is that the movement of the particles is the thing that causes the pressure, which of course we hopefully understand. So actually I have this example here I have seen for myself, and if you ever have a chance to be in a high energy laser lab, you will see that you could see this for yourself as well. But I worked in a high energy laser lab that had what is called a pulse laser, and this pulse laser would shoot a beam of ultraviolet light 10 times per second. And this beam of ultraviolet light was rather energetic and rather dangerous, actually. If you walked through it, it would bleach your clothes. If you put your hand in it, it would bleach your skin. It would essentially evaporate. Excuse me. It would evaporate the pigments in your skin, and it would hurt. It actually hurts quite badly. It's a very dangerous. If it hits you in the eye, it blind you permanently. So it's quite a dangerous laser. And so what we did is we would block the laser with a piece of aluminum, and it was just an aluminum piece of 1/4 inch aluminum that was bent. Actually, it was 1/8 inch aluminum, but it doesn't matter, I guess. 1/8 inch aluminum bent in an L shape, and then we would bolt that L shape to the table so that it was sticking up into the beam. But when the laser was on and pulsing and hitting that beam, what we call that beam stop, you would hear a ringing because the laser was actually pushing against this this beam stop. So it was actually causing a pressure on the beam stop. Here they're going to do the same thing with an electron beam, a high energy electron beam. So here we have a beam of electrons moving in the positive x direction, and they hit a target in a vacuum chamber. If 1.25 times 10 to the 14 electrons traveling at a speed of 3 times 10 to the 7 meters per second strike the target during each brief pulse lasting 5 times 10 to the 8 minus seconds, time to the 10 to the minus 8 seconds rather, what average force is exerted on the target during the pulse? And then we want to assume all the electrons penetrate the target and are absorbed. Then what average pressure is exerted on the beam spot, which has a radius of 4 millimeters. So there they give us an area, right? So here we go. Average force is going to be just like we calculated previously, except we're not talking about a gas here, we're talking about electrons. It's going to be the number of particles times the change in momentum times delta T. Well, the change in momentum, its final momentum, since the electrons get absorbed by the target, is 0. So the change in momentum is going to be 0 minus the initial momentum. And that's what they have here, 0 minus initial momentum. And then they have, for their delta T, it's going to be 5 times 10 to the minus 8, because that's how much time it takes for these things to get in there and hit the target. And then they plug in the mass of the electrons, the number of the electrons, and the speed of the electrons, and they get 0.0683 newtons of force applied on that target during that pulse. To calculate the pressure, you just divide that force by the area of the circular beam, and since they tell you the radius, you can calculate. Make sure you put it into meters. That's all they really do. Calculate that pressure, 1.36 times 10 to the 3 Pascal. Now, pressure is directly related to kinetic energy. We've just figured this out. However, pressure is also part of the ideal gas law. And so if we take our equation that we just calculated, which was P equals 2/3 N over V, and we multiply both sides by V, we get PV equals 2/3 N, 1/2 mV squared. And PV is 1/2 of the ideal gas law. So if we set this side of the equation equal to the other half of the ideal gas law, and then divide by N and K, which are the number of particles and the Boltzmann constant in the equation, then we get this equation for temperature. And look at this. Now temperature is directly related to kinetic energy. And it's absolutely true. Temperature is directly related to the movement of the particles in the terms of the kinetic energy of the particles. And this is the equation for it. So equation 10.14, 10.15, you need to have those in your head. You can also take that kinetic energy, 1/2 mv squared, right, and set it equal to nRT, the other side of the ideal gas law, and then you can assume that the internal energy, which would be the kinetic energy of the gas, is going to be equal to 3/2 nRT, so the internal energy of the gas is actually directly related to temperature, which I already intimated to you, that the internal energy of a gas is measured by measuring its temperature. But here is the confirmation, and here is the equation for calculating the actual internal energy of the gas once you have its temperature. And this is for a monoatomic gas. So essentially, this is for a gas that only has one atom as its gas molecule. So the types of gases that would work for this would be, helium, for example. Helium just has individual helium atoms. Hydrogen wouldn't work out so well because hydrogen is 2 hydrogen atoms in a diatomic molecule. So this only works for monatomic gases. For diatomic gases, it changes things a little bit. But from these equations now, previously, we can solve for the velocity of the particles. So the velocity of the particles is equal to 3 times the gas constant times temperature over the mass of the gas with a square root over the top. Or 3 times the Boltzmann constant times the temperature of the gas over the mass of the particle, mass of the atom, with a square root over the top of it. So this can help us to calculate the speed of particles at different temperatures. And it's not the absolute speed, it's actually the average speed. But it's a very good approximation for the speed of particles at particular temperatures. So for example, hydrogen at room temperature, which is about 300 Kelvin, we would put in 3 times the gas constant, 8.31 joules per mole Kelvin, multiply by room temperature, which is about 300 Kelvin, and divide by the molar mass of hydrogen. So the molar mass of hydrogen is 2.0 times 10 to the minus 3 kilograms per mole. And we find out that the RMS speed, or the average speed is what RMS means root mean squared. But the average speed of hydrogen at room temperature is 1.9 times 10 to the 3 meters per second. It's about 2,000 meters per second. And that is pretty typical for most gases at room temperature. The gas in the air in the room that you're sitting in now is mostly nitrogen, and it will be a little bit slower than hydrogen, but it'll still be up in the 1,000 kind of meters per second average speed. Atoms that are in gas form move very quickly at normal temperatures. Here they have the average speeds of some gases at room temperature. So for hydrogen gas, it's 1900. For helium, it's 1300. For water, it's 600. For neon, it's 600. All up in the hundreds here. A couple of them in the thousands. Of course, the smaller the gas, the faster they go. The bigger, the slower they go. But move pretty quick. Here they have, this right here is a graph of the speeds of gases at 300 Kelvin, but now it's a distribution. So you can see that most of a gas will be here at this 400 meters per second in particular conditions. But some of them will be going slower, so some things are over here. There's some speeds up here as well. So not all of them are at the average speed. A lot of them are, but there's a lot of spread in the possibilities here for 300 Kelvin. But at 900 Kelvin, notice that the average speed increases, and also that the spread actually increases. There's a lot more going a lot faster, and there's actually less going slower, right? But a lot more out here in this fast region out here, faster and faster speeds for this particular gas, which I think is nitrogen. They've got it for. So, let's take a look at example 10.10. We had a cylinder of helium. It's at 20 degrees Celsius, which is 293 Kelvin. There's 2 moles of it in the cylinder. And the helium behaves like an ideal gas. We want to find the total internal energy of the system. We want the average and we want to find the average kinetic energy per molecule. We don't know how much energy would have to be added to the system to double the speed of the molecules. And then they tell us the molar mass of helium is 4 times 10 to the minus 3 kilograms per mole. So, total internal energy of the system, that's the equation. It's U equals 3/2, 2 times 2 moles times 8.31, which is the R, times the temperature, which is 293 Kelvin. We just plug all those numbers in. And this is for a monatomic gas. So, and it just so happens that helium is a monatomic gas, so we're good to go. You end up with 7.3 times 10 to the 5 joules, a fair amount, 10 to the 3, 10 to the 5 joules. What is it? 10 to the 3, it looks like. Joules. Then they say, what is the average kinetic energy? Well, we use the equation for kinetic energy, which is the 1/2 mv squared, but the kinetic energy is also equal to 3/2 times Boltzmann constant times the temperature. And that's the side of the equation that we'll use because that's the side that we actually know the numbers for. We know K, we know temperature, and 3/2 is just 3/2. So we plug those numbers in and we get 6.07 times 10 to the minus 21 joules. And then they say how much energy must be added to double the RMS speed. Well, in that case, we need to set up our equation so that we have a difference in internal energies And here they've got those equal to a difference in temperatures, and then they solve it, or they don't solve it, but they show it as a change in temperature here, right? And let's see here. So how much energy must be added is going to be this difference in energy here. So we're solving for that here. We end up putting in our numbers here, and here's the trick in this last part right here. This first line shows that we have our difference in energy equals 3/2 nRT final minus 3/2 nRT initial. Then they go ahead and they factor out the 3/2 nR, and they just get T final minus T initial. And you can see here that the only difference between the original energy and this energy that we're looking for is going to be this change in temperature. And if we want this change in temperature to double it, then this change in temperature is going to have a 2 involved, and it's going to have to be a double amount. And so what you got to do here, is it double that they want? Double. I'm actually not convinced that that is 100% correct. Why am I not convinced of that? They're saying that they're using equation 10.18, so I'm going to go to equation 10.18 really quick and see if I'm convinced of that. 10.18 is this one. Okay, so that makes sense. So from this equation, to double the speed, which is what we need to do, we need to quadruple the temperature, because if we quadruple the temperature and then take the square root, then it will be doubling the speed. And when we double the speed, then we're going to be satisfying part C here, which is where they want us to double the speed. So to double the speed, we have to quadruple the temperature. And so you end up with a 3 out here. Well, you don't end up with a 3 out here. You end up with 3 times the original energy, or 3 times the original temperature, and that gives you twice the speed. And I guess the tricky thing here is to realize that you can't do this just from one equation. You have to calculate the energy from this equation, but you have to figure out how much temperature it's going to have to change from equation 10.18. What does part D want us to do? I forgot. Oh, there's no part D. We're good to go. So, that is the end of chapter 10 with our treatment of the gas law, or treatment of a gas from the molecule's point of view in the kinetic theory of gases. The 2 things that we really get out of the kinetic theory of gases are that, well, the 3 things, I guess, is that the pressure is directly related to kinetic energy, the temperature is directly related to the kinetic energy, and that the velocity can be calculated from the temperature. The velocity of the average velocity of the particles can be calculated from the temperature. The other thing that we're going to get from it in the next chapter is that the pressure and the temperature both contribute to the internal energy of the gas. We'll learn that in the next section. So let's go ahead and take a look at the homework for this one, which is 10.5, I guess. Three questions. So what is the average kinetic energy of a molecule of oxygen? Well, remember that there is a combination of those equations that we just looked at in that section that will give you 1/2 mv squared on one side, which is the kinetic energy, and it will give you something including temperature on the other side. So you can find that equation and you'll be good to go there. In problem 2, you have Superman leaps in front of Lois Lane to save her from a volley of bullets. In a 1-minute interval, an automatic weapon fires 156 bullets, each of a mass 8 grams and 360 meters per second. This is just like the electron beam example, except it's bullets, not electrons. So you do it just the same way it's done in that example. And then number 3 is a tutorial exercise where you have nitrogen molecules striking the wall 9.1 meters centimeters squared. So you know the area of the wall, you know how many are hitting it. You also know the time, the change in time. You have the velocity, so you're going to be able to calculate the change in momentum and the distance. So that's very much like just building up that kinetic theory of gases at the very beginning of section 10.5. So they should be able to guide you through that pretty easily. Any questions involving the end of chapter 10? Okay then. Well, we're done with chapter 10. We will start chapter 11 on Monday. I believe that's what we're set to do on Monday. Looks like it. So I bid you a fair weekend. You guys are meeting today at 5 o'clock to do your lab, is that correct?
I think so. I'll have to text Sydney and see if she's staying at my back or not.
Okay. Try to get together and do those labs because we got quite a few of them to do here in the next week or two. And then tell me of your progress. Any other questions? All right. Well, have a good weekend. Good luck finishing all the homework in the labs and everything else, and we'll see you later.